We kind of went through homework 1 and did a little bit more, and I gave you guys homework 2, right? Is that right?
Sounds about correct, though.
Where we did the addition, subtraction, division, right? Those were the things we talked about last time. Okay. Do you guys want to take some questions from homework? Well, really 1 or 2. I'd be happy to do stuff from either one of those. I assume most of the questions will come from 2 because we already kind of talked about homework 1, but if you got some more homework 1 stuff that you want to ask about, that's cool too. Claire? From homework 2? Sure.
Can I hit the lights, Mr. Coolidge?
Absolutely.
Love to see it.
I love that. I love that. Like, absolutely. I'm going to keep saying that my whole life. Like, I just love that word.
It's so silly.
I just want it reminds me of like Fruit Loops. Like,
Yeah, Fruit Loops sounds so good right now.
right?
Okay. So, here we have a multiplication and division problem. So I've that we would have talked about last time, and with a division problem that we would have talked about in that same lecture. What I'm going to do is I'm going to start by just doing some prime factorizations. So I'm going to do the prime factorizations first, and then kind of figure out whether I want to put things under the same radical or not afterwards, because I'm not right off the bat totally sure what I'm going to want to do. So that's 4 2s and a 13. And I think I'm just going to go ahead and do that, I guess. And what do I have here? 3 squared and an 11. Actually, I'm going to hold off on that. And then 8 19. 3. Okay. So we have 3 squared times 7 times 13. Okay. So I'm going to put this all under one radical to start with, because I'm going to do some reducing right away to get rid of that stuff. So far, so good, Claire? Okay. So if I look here, let's see, I have 1 packet of 3 for my 2's. This second piece here I can think of as 2 to the first, times 2 to the third. So I have like a second packet of 2's in my numerator. And I have 1 2 left in my numerator then. So far, so good?
Wait, what number did you cancel out with the denominator is like 3 squared times 1?
That was an 11. That canceled with the 11 in the numerator. And then if I look at the denominator, well, I have 4 3's, so I'm going to think about that again. It's like 3 squared times, or 3 to the third times 3. So there's another packet of 3 3's. And then I have that 3 and the 7 left in the denominator. So far, so good? Okay. So now what I'm going to do is I need to rationalize my denominator, because I have this radical in my denominator. I have the cube root 3 and the cube root 7 still left there. For me to get rid of those, I need packets of 3 inside my cube root. So right now I have 1 3 in the denominator, so I would need 2 more 3's to get to 3. And the same thing with my 7's. I have 1 7 in my denominator. I'm going to need 2 more to get to 3 7's. So that's me rationalizing the denominator. Yipes. So I'm going to have 4 thirds. And then I have 2 times 3 squared times 7 squared. And then I have 3 to the third and 7 to the third now. Hi.
Hello.
How are you?
I'm good. How are you?
Oh, just fine. Ashley Quinn, it's for you. Yep, I think they want you right now. So far, so good, Claire?
Yeah.
Okay, and now I notice that I have packets of 3 in my denominator, so each of those can come out. So I have the 3 from out front before, I have the 3 that was underneath, and the 7 that was underneath. And then if you wanted to, we could simplify this all down. So let's see, what is that? 9, I'm not doing it. I'm doing it in the calculator. 882 over 63. And that's probably as good as you could do on that one. So again, the bad part was having to rationalize the denominator there. Before that, it should have been okay. But the rationalizing the denominator piece can be tricky sometimes. Does that feel okay, though?
Yeah.
Do we have some follow-ups on this one, or somebody have a new question? Megan?
I kind of get lost after
Okay. So this piece right here? Okay. Do you understand why we're doing that? Okay. So let's explain why. So I'm just going to do like a little aside here. So you remember last year in your geometry class where you did like sine, cosine, and tangent stuff? You guys did that last year, right? So if this is my angle theta, and let's say this is a triangle that has side lengths 2, square root 3, and then, oh, let's not do it that way. Let's do 1, 2, and then this would be square root 5. And we did like, you'd say like, okay, sine theta is opposite over hypotenuse. So that's like 2 over square root 5, right? But we didn't leave our final answer that way because we decided that we weren't going to leave any radicals, any square roots in the denominators of our fraction. So you would have multiplied the top and bottom of this by the square root of 5 to say your final answer would be 2 square root 5 over 5. You kind of remember doing that last year? We're doing the same thing here in this step. Okay? So really what we have is 4/3 times cube root 2 over cube root 21, right? I have that radical in my denominator that I don't like. So I'm going to get rid of it doing the same thing that we would have done last year in our geometry class. The difference, though, is that instead of working with a square root, this time we're working with a cube root. Okay with that? So instead of needing pairs of things to cancel out the square root, I need triples to cancel out the cube root. So when I looked at my denominator, I saw I had 1, 3. So to cancel it out, I needed 2 more. And I had 1, 7. So to cancel that out, I needed 2 more 7s. Is that okay? So then I just gather into the same radical. Is that okay? So again, I just have the 3 cubed and the 7 cubed now is really the only thing that changed, right? And then inside the numerator, I have the 3 squared and the 7 squared, right? And then I reduce the denominator. So I have that 3, and I have that 7. And I can't do anything to the numerator because I don't have any triples in there. So then all I did at my final step was just multiply the things together to get to the end. Did that help? Okay. You're welcome. So again, I tried to connect it to something we're already familiar with doing there to start with, to just kind of show you that it's still doing the same kind of thing. It just, the context is a little bit different because it's a cube root instead of a square root, but same idea. Joe.
Can we do number 7, please?
On homework 2?
Yep.
Sure. If it wants to move for me. Is that on the first page, Joe?
I believe so, yep.
Okay. It's being so laggy. Okay. Okay, so I'm going to start by doing a prime factorization. So the 2, I don't have to do anything with. 72, I noticed, actually I'm not going to do a prime factorization for 72 because I noticed that's 36 times 2. And 36 is a perfect square. So I'm just going to write that as 6 root 2.
Okay.
Is that okay?
Yeah.
And then for 32, again, I could do my prime factorization. So maybe I should do it. Yeah, we'll just do it. All right, so 432, let's see, that's 2 and 216, and that's 2 and 108, and that's 2 and 54, and that's 2 and 27, and I'm just going to put this stuff all under the same radical. So there's the 2 to the 4th, and then 27 is 3 to the 3rd. Are you okay with what I did there, Joe?
Yep.
Okay. So what I'm doing is I'm looking for packets of 2 for the square root. Well, 2 to the 4 is really 2 squared and 2 squared. And 3 to the 3rd is really 3 to the 1st and 3 to the 2nd. So these pieces are all packets of 2. So those are going to come out. So I still have my 2, still have my 6. I have another 2, I have another 2, and I have another 3. The things that are left over then are the 2 and the 3 that didn't have a pair to go with. So far, so good?
Okay, so the numbers that have a pair to go with, those are going to go before the square root?
Right, so those are the ones that bump out.
All right, okay.
And the numbers that aren't pairs have to stay because they don't have you can't cancel the radical.
Right. Makes sense.
So then all I'm left to do is multiply stuff together. 2 times 6 times 2 times 2 times 3 is 144. And then 2 times 3 is 6. And there we go. Yeah. I was looking at that for a second to see. I saw the 144 and noticed that's a perfect square. I was like, oh, maybe there's a really clever, quick way to do this, but no, I don't think there is because that 2 coefficient out front, it's really, yeah, it's really not that much. So it's like 72 or whatever. That is really all that we pulled out of there, so that's not so good. All right. Who else? Meg?
Could you do
20? That's the last one? Okay.
Okay, that one was interesting.
Yeah, I'm just looking at it. It seems like it's gonna be-
Sure. So, for sure, we're going to want to start with a prime factorization because this looks pretty nasty because the numbers are kind of big. So 25 is 5 squared. 320 is going to be the same as 32 times 10, right? 32 is 2 to the 5th, and 10 is 2 times 5, so that's going to be 2 to the... Don't feel bad if you couldn't do that, or didn't see to do that in your head. That's what you get as a math teacher. And the next one is we have a 3 to the 6th times 5. Yeah. And the last one is 5 to the 4th. Everybody's okay there. Now, ordinarily, I would reduce these radicals and then try to combine like terms here. But I noticed there's a shorter way to do this problem. So if I look, this has a packet is 2 packets of 3 already. This is 2 packets of 3 already. And this one is like a packet of 3 and then a leftover 5, right? So the pieces that I don't have a full packet on are just these 5 to the 1st, right? So I'm putting in 2 more 5s to each place, which means I'm going to have all of them full packets of 3, right? Which means that when I reduce the radicals, there's just going to be no radical left. So I'm going to go ahead and do that because that seems like a pretty good deal to me. Write down what I have. You don't really need to write this step because you could go straight from what we had before to our answer, but I'm going to write it just so it's clear. Is everybody okay with what I wrote down there? So instead of writing 2 to the 6th, I wrote it as 2 packets of 3, right? Instead of writing as 3 to the 6th, I wrote it as 2 packets of 3. And instead of writing 5 to the 6th there, I wrote it as 2 packets of 3. Just so it's clear when I do my next step that I have 2 times 5 plus 3 times 5 minus 5 times 5.
Tell me what to do.
That's it. So when I type that in my calculator, I get 40. And that's my final answer. So it's one of those that it was really nice that I noticed in the beginning that if I just multiplied first instead of adding and doing the adding and subtracting, I got rid of all the radicals and it became a pretty easy to handle problem. It would not have been wrong to reduce the radicals and combine the like terms there and then do the multiplication. That would have been kind of the natural thing to do. You still can get to the right answer, but it's kind of like the scenic route. You would have gotten to see a lot. You got to do a lot more math doing it that way, which is fine. Megan, is that okay?
Yeah.
Did you follow what I did and why I did something different than what I usually would have done? And it was a nice shortcut to observe, right? It made this problem quite a bit neater to do. I don't know if it made it easier, but it was certainly neater. And probably a little quicker, right? What are you, stretching or questioning?
Question.
Go for it, my dude. 15? Sure. Is that on this same page? Yes. Okay. So I'm going to start with prime factorizations. So 32 is 2 to the 5th, and 128 is 2 to the 7th. To reduce the radical, I'm looking for packets of 2. So 2 to the 5th is really 2 packets of 2, and then just a packet of 1. 2 to the 7th is 3 packets of 2, and then a packet of 1. So when I reduce the radicals, from the first radical, I have 2 2's that can come out front. And then I have the 1 2 that's left over. Cool there. In the second radical, I have 3 packets of 2 that I can take out. So I have 3 more 2's out front. And then I have the 1 2 left over that has to stay. So then if I multiply this out, I have 12 root 2 plus, which is 52 root 2's. No problem. Is this starting to feel a little bit more manageable as we're doing these? I know this is not particularly the easiest skill in the world, right? It takes a little bit of getting used to, but hopefully it's starting to feel a little bit more comfortable. Joe?
So if you get 2 different square root symbols, like a square root 2 and a square root 5, I don't know if that can even happen, but if it does, do we add the square roots together, or do we choose the larger one? Or?
So as an aside, if we have the square root of 2 plus the square root of 5, there's nothing to do in that case.
Yeah, we don't know that.
Yep. So there's no addition that can be done. I don't remember if I had an example where that happened in the homework here, but it certainly could come up.
All right.
And there's just, if you've reduced the radical fully and there's nothing more reducing you can do and they're still not the same, they can't add together.
Okay.
We can multiply and divide them still, and we haven't talked about how to do that yet, but that is coming.
All right.
Not today, but the next lesson we'll kind of start getting into that, how to deal with unlike radicals. But there is a way to deal with that, and it's not terribly difficult, but it's, it's more than I want to get into for today, as I still think we're worried about like radicals for the time being. You know what I mean? Okay. Any other questions about this for me? So if you look at the content library, I have a homework 3 already loaded in there, which is just some more practice on these 3 topics that we've been working on: multiplying, dividing, and adding and subtracting of like radicals. I think that we'll just spend the rest of our time today giving you a chance to work on this stuff in class so you can get some immediate feedback if you're having questions on what you're doing, or if things are going well or not well, or you got stuck someplace. And sound okay to you guys? Okay. So I'm just going to let you go. I'm going to stop the recording.